All gathered here. Greetings from PG and Research Department of Physics, A.V.V.M. Sri Pushpam College, Poondi, Tanjavur. Now the webinar K. Thirumurugan, Assessor, PG and Research Department of Physics to deliver the welcome address.
Good morning to all. First of all, I welcome all the participants from South India, especially Kerala, Karnataka, Telangana, Andhra Pradesh, and our students and friends. The conference is going on the topic Emergent Properties of Self-Assembled Nanocomposites. The eminent scientist and professor Dr. R. Muralidharan going to give you a lecture on this topic. First of all, I thank our Chief Patron Sriman K. Tulasiya Vandayar, Secretary and Correspondent of our college, A.V.V.M. Sri Pushpam College, for giving the opportunity to do these kind of interactions with the eminent scientist and Dr. R. Shivakumar, the principal of our college, the convener and the HOD of physics, Dr. K. Ravichandran. Friends, I welcome all. Thank you.
Shall I proceed, sir?
KR sir,
yeah, sure, sure.
Dr. R. Muralidharan is an eminent scientist who is working in Welltech High Tech Engineering College, Avadi, as a professor of physics, who did UG in 1993 in our A.V.V.M. Sri Pushpam College, and PG in Bharat University in 1995, and did PGDCA in 1997 in Bharat University, and he did PhD in August 2000. He completed PhD in August 2004 on the topic of crystal growth and characterization of rare earth metal ions doped triglycerin sulfate and nonlinear optical single crystals. As his advisor, Dr. Eminent Scientist P. Ramaswamy in Anna University, India. He did postdoctoral experience. He having postdoctoral experience of 7 years and teaching experience to till date 8 years 6 months. He served as a postdoctoral research fellow in Spain, Korea, and Leeds University, UK. Dr. R. Muralidharan is thin films, new multiferrite materials and characterizations, sputtering, multiferrite nanostructures, self-assembly oxides on silicon, single crystal growth, polycrystalline multifunctional, ferroelectric, piezoelectric, and sustainable. 2 universities of Tamil Nadu, Anna University, Chennai, and Bharatiyar University, Coimbatore. The countries visited by our guest: Germany in 2010, Italy in 2010, Tokyo in Japan 2015, and the UK, Spain, Korea. Thank you.
Thank you, Dr. Thirumurugan, for your kind introduction. I thank the organizers for giving me this opportunity to present my research work to this audience, to this profound audience. I thank Poondi College management, especially the HOD of Physics Department, Professor K. Ravichandran sir, for giving me this opportunity to present my research work to this audience. So, and also, I'm proud to say that I'm the alumni of Poondi between 90 and 95. I did both my UG and PG in Poondi College. Okay. So with that, I will get into my talk. The title of my presentation. Can you all hear me? Can you hear me?
Yes, sir. Yes, yes.
Okay, okay. So the title of my presentation is the emergent properties of self-assembled nanocomposites. In this presentation, I'm going to briefly introduce about what are the emergent properties. What are the emergent properties, and why it is so important. And then I'm going to tell about what is self-assembly, and why self-assembly is very important nowadays. And then nanocomposite, everybody knows. My college conducted. So before getting into the talk, let me start with one of the famous quote by Wolfgang Pauli, almost a century back, yeah, around 1930s. He quoted this one, like God made solids, surfaces were the work of the devil. Okay. So when you want to measure the properties of the solids, at the surfaces, at that time, at the surfaces, the property will change. At the edge of that solid, because from the surface of the solid, because the atoms change at the surfaces. Okay. So at that time, he proposed that the surfaces were the work of the devil, because the core property of the solids were very difficult to measure. Now we can consider the interface. There is a main difference between surface and the interface. Okay, so I will tell the difference maybe during my presentation. But nowadays, both the surfaces and the interfaces become very, very important when you are especially working on a nanoscale. And surfaces have become very, very important as we are working on a minute nanometer scale. Okay, so throughout this presentation, I'm going to talk about the importance of the interfaces and the surfaces, and how they are giving new properties, that is, agents are available on the core of that material. Okay. So throughout the material, throughout my presentation for the next maybe 40 or 50 minutes, I'm going to talk about work on the surfaces or the interfaces. Okay. So the overview of my presentation is like this. First, I will present about the strain engineering. Okay. Most of my presentation will be on the strain engineering. So I'm going to present the lattice mismatch between the thin films, substrate on the material. Okay, so on this one, so it says if your material, the lattice parameter of the material is different, then you will have to have epitaxial growth, you will have a tensile strength, and there will be a compression here. Okay, so this is called as heteroepitaxy. Okay, so you have two materials. Okay, you have two materials with different lattice parameters, so that is called as heteroepitaxy. So most of mine will be on this heteroepitaxy. Okay. So, and then at the end of my talk, I'm going to introduce a bit about the interface engineering, the recently evolved field of interface engineering. So when you put two solids of different properties at the interface here, you will get a completely new or a completely different property. Okay, I'm just going to give a brief introduction about this one. This is just the evolving field, and then I'm going this composition engineering. This is well known. Okay, like on the well known piezoelectric material, lead, zinc niobate, and lead titan. When you change the composition, okay, one of the material is in the rhombohedral structure and another one is in the tetragonal structure. So if you change the composition at a particular composition, this is called as a morphotrophic phase boundary. At that phase boundary, you could see the emergence of new properties or the enhancement of those properties. Okay, so we can tune the emergent properties by composition varying, also composition engineering also, but I am not going to touch on this one now because I am going to concentrate only on the nanocomposites. So I will be concentrating mainly on the engineering. Now it's fine. Okay. So I'm going to concentrate on this strain engineering, and I'm going to present mainly on the emergent property of multiferrites or magneto-electric coupling. Okay, so before getting into my presentation, I just wish to thank my mentors, my gurus on the research. Okay, so Professor P. Ramasamy and Professor Jayvel are my PhD supervisors. Still, I'm working with them. Very eminent and well-known professors. Not only in India, throughout the world, a well-known crystal grower and very kind person, Professor, both of them. And during my postdoctoral position, I just worked on Korea. I spent a mentor in Korea. He's Professor Uni Jong. So I learned multiferroism from him. I started working on multiferroic materials from him. At that time, it was the signs on multiferroics were blooming. And then I spent almost 3 years in Barcelona, Spain, with Professor Font Cuberta. He's the student of Professor Gudenev, who got a Nobel laureate, who is a Nobel laureate last year, Professor J.B. here. Okay, so Professor Font Cuberta, he has a collaboration with 2 Nobel laureates, one with Professor J.B. Gudenev, who got a Nobel Prize for lithium-ion battery last year, and then Professor Albert Fort, who got a Nobel Prize in the year 2007 for spintronic materials. Okay, so most of the presentation, most of the results which I am going to present here are the work which I have done on Spain with Professor Font Cuberta. And then the Professor Bill, he's a well-known person on piezoelectric materials. So I learned in the last part which I showed on the composition engineering, I learned from him, but I'm not going to present on this work. I'm not going to present the work which I did in UK. So most of the work which I will be presenting here are the work I have done on my stay during my stay in Spain. Okay. So these are the fields these people influenced me. In general, I'm interested in mainly on material science, all sorts of materials, but during my PhD, I worked on single crystal growth with Professor Ramasamy and Jayvel, and then most of my work on multiferroics I started in Korea, and then this work self-assembled and nanostructures I worked on. I started working on Spain, and I am still doing on that one. And lead-free piezoelectrics. This is the influence of Professor Andrew Bell. Now I'm concentrating on these kind of materials called photoferroelectrics and hybrid energy harvesting. Okay. Okay, so this is one of the well-known picture, which is on the field of multiferroics. Okay, so this is the electric polarization, and we can switch the electric polarization by applying electric field. So this group of material is called as ferroelectric material. Okay, so this is a strain, and you can switch the strain by applying stress. So this group of material are called as a ferroelastic material, and this is a magnetism, ferromagnetic material. So you can switch the ferromagnetic polarization by applying magnetic field. So this class of material is called as a ferromagnetic material. So the cross coupling between these two is well known. This is our piezoelectric material. So cross coupling between the electric field and the strain. This is called as a piezoelectricity. And the cross coupling between your magnetization and the strain. This is called as magnetostrictive materials. These are all well known, but to have the cross coupling between the magnetic field and the electric field is very, very difficult, or it is very, very rare to have this kind of coupling. Okay, so where you can switch the magnetic polarization by applying electric field, or you can switch the electric polarization by applying a magnetic field. So this has found these materials are called as a multiferroic materials, and this has found excellent properties in the spintronics and other recent devices. Okay, if you want to increase your memory applications, or if you want to, as the electronic transistor devices size is becoming smaller and smaller, so we can't go on the traditional way, so we need to switch our technology to the other way. On that scale, these multiferroic materials are very important. This is not the only thing. So instead of on this plot, instead of ferroelectric material, if you put electrocaloric materials here, or if you put magnetocaloric material here, you apply electric field, you can start cooling your region. That is called as a solid state cooling. So that is also one of the emerging field. That is also one of the emergent properties where you can get the cooling. Okay, solid state cooling. That is one of the emergent field. I'm not going to touch on that one, but that will be future work. Okay, so this plot gives the magnetically polarizable circle, where you are having paramagnetic, and then this one is a ferromagnetic circle, which is a part of a magnetically polarizable circle, and we have a overall electrically polarizable circle, and then on which a part of that is the ferroelectric materials. Okay. So the cross coupling between the ferromagnetic materials and the ferroelectric materials are called as multiferroic materials. And among which magnetoelectric is one of the subclass, which is another important class of material. So in this presentation, I'm going to tell you why this getting a multiferroic property at room temperature is very difficult, and then I will switch to how we can overcome that with the effect of strain engineering. Okay. So in this periodic table that we all know that the magnetism comes mainly from these class of materials, like manganese, iron, and cobalt. Okay, where you need the d orbital should be half filled. Okay. And the ferroelectricity comes mostly from this class of material, titanium, tantalum, vanadium, these class of materials, where your d orbital is completely filled. So there is an exclusivity between your ferromagnetic materials and ferroelectric materials, even on the elemental scale. Okay. And also, on the long range ordering, if you want to switch your magnetic polarization, you need to reverse the time reversal. Okay, so you need to switch the electron spin state, which is called as a time reversal. Okay. And then if you want to switch the electric polarization, you are going to switch you are going to inverse the space polarization, okay, space inversion. Okay, so in the case of multiferroic materials, you need to inverse both the space and the time inversion, which is very difficult to have this both the space and time inversion in the same class of material. So that is why having a multiferroic material is very rare, and that too in the room temperature, having this property is very difficult. Okay. Throughout my presentation, I'm going to present on a special class of material called the perovskite materials, which has a very simple structure like A.V.V.M. Okay, so there is A site, there is B site with octahedra here. Why this class of material are important? Because we have quite enormous kind of properties on this simple crystal structure. Okay, so if you want to have insulating materials with the ferroelectric properties, you do have like lead titanate, barium titanate. You can also have conducting materials like a lanthanum strontium manganate with the ferromagnetic property. You can even have a superconducting material and a simple strontium titanate. You dope a little bit of lanthanum, that will show superconducting property. And this one is a small octahedral rotation. This octahedral rotation will create antiferrodistortive order, which is strontium titanate and calcium titanate are some of the example for this antiferrodistortive order. Okay, and also on this class of material, you can have the charge ordering, or spin ordering, or orbital ordering, or lattice tune. So you can tune this class of material to produce enormous properties, a lot of properties for a lot of application, for like a charge orbital ordering, or spin orbital ordering, or a lattice charge coupling. All these kind of two order parameter or two instabilities combining together to give new or emerging properties. Okay. So that's why this simple class of material is very important, and it gives excellent properties. Okay, so this is one of the first reported magnetoelectric material, single phase magnetoelectric material around the Néel temperature, around 25 Kelvin. The dielectric constant shows some anomaly here. Okay, so that means that you are having a coupling between your ferromagnetic magnetic and then your electric polarization. Okay, actually this is an antiferromagnetic material. This is not a ferromagnetic material, and the Néel temperature is around 25 Kelvin. So even then it has that kind of coupling. So we call this as a magnetoelectric material. Okay. So in the case of composites, around 1975, they reported that cobalt ferrite and barium titanate composite can give this kind of magnetoelectric coupling, because barium titanate is one of the well-known piezoelectric material, and cobalt ferrite is one of the well-known magnetostrictive material. So they put together to show that it shows a very good magnetoelectric coupling. Okay. So this is on a ceramic scale. So, and between 1975 and 2000, there was a dormant research on in this field, because to get this kind of material with a very good magnetoelectric coupling is very difficult. So around 2000, this field started evolving back again because of we can prepare excellent thin film materials, and then we can, as I'm going to present in this work, in thin films you can work on the strain to produce different properties than the bulk materials. Okay, so I'm not getting into the details of this one. Okay, so the multiferroics can be classified into different class for on single phase materials. Okay, but I'm going to take only this material, bismuth ferrite, lone pair mechanism, because you can see here this has almost like 90 microcoulomb per centimeter square, which is one of the huge electric polarization, one of the best material on ferroelectric polarization. Okay, but throughout my presentation and this presentation, I'm going to concentrate on this heterostructures, multiferroic heterostructures, and on this also. There are three types of heterostructures, composites you can call. One is called as 0-3 heterostructures, in which one of the composite is on the 0 dimension and another is on the 3 dimension. And this one is called as 2-2 heterostructure, where two materials are on the nano dimension in the on the 2 scale, and this is called as a 1-3 heterostructure, where one component will be vertically aligned on the another one. So one will be like a rod and another will be like a matrix. Okay, so I'm going to concentrate one this one, because there are some disadvantages on these two classes of materials. Okay, so if you take this class of materials, when you put up a layer here, so this the substrate will couple with this structure. Okay, so as I mentioned in my introduction, so these are coupled through elastically. Okay, so I will explain that later. So when it is not elastically coupled, then to have the magnetoelectric effect is very difficult. So that is the problem with this one. Okay, so for that purpose, we are concentrating on these nanorod type materials. Okay. So as I said, bismuth ferrite is one of the well-known materials. So we are going to take one of the component as bismuth ferrite because it has a very huge electric polarization. The problem with the bulk is it is antiferromagnetic. Again, as I said during the introduction, to have the multiferroic material, you need to be have a ferromagnetic property. But if you put this bismuth ferrite on a thin film, that shows ferromagnetic property. Okay, so in thin film, because of the lattice strain, so you can convert the antiferromagnetic property to the ferromagnetic property. So I'm going to take one component throughout my presentation. Bismuth ferrite will be one of the component material. Okay, so this is one of the earliest presented reported multiferroic heterostructures, which is on 2003 in Science by a famous group of Ramesh, barium titanate and cobalt ferrite, which is epitaxial thin films. Okay, so this shows the X-ray pattern of this heterostructure. So this is the substrate peak O2, and then strontium ruthenate, because they are going to measure the conductive property. For that, they put a small thin layer of strontium ruthenate, over which we are having they deposited barium titanate and cobalt ferrite. Okay, so this is epitaxial. There are no secondary phases. That is very clear from this one. On the TEM image shows a clear ordering of cobalt ferrite rods on a barium titanate matrix. Okay, and then this is the sand pattern, which is clearly shows that these are all highly crystalline, barium titanate and cobalt ferrite. This is the A.V.V.M figure. That's well known. It's very clear that it shows a very nice structures. Okay, so on this material, it is clearly shows that it is a electrically polarizable. Okay, you can apply electric field, you can switch, and then magnetically polarizable. And this graph shows the temperature with the magnetization. We all, this is on the Kelvin scale, so we all know that barium titanate, the transition temperature is around 120 K, so 120 degree centigrade. Okay, so around that ferroelectric transition, the magnetic the magnetization, it shows some anomaly. That means it the magnetic polarization is coupled with the electric polarization. So that's the confirmation of this one. Okay, so magnetically it is the EC axis is on the out of plane, so I'm not getting into the details. Okay, so later on they reported on this material, bismuth ferrite and cobalt ferrite and nanocomposite, because as I said in the beginning, bismuth ferrite has a much more electrically polarizable than barium titanate, and again this clearly shows that your bismuth ferrite and the cobalt ferrite are crystalline in nature, and then the high resolution TEM clearly shows the interface, very nice interface, and they are highly epitaxial. Okay, so this is the A.V.V.M image where before before polarization, you can see all your magnetic domains are posed on one direction, and then after applying electric field, you can switch the magnetization to the another direction. There are some the black dots here, the black dots here changes to white on this side. So that shows that on this material, on this bismuth ferrite, cobalt ferrite nanocomposites, you can switch the magnetic polarization by electrical polarization, and this is the piezo force microscopy image, which also tells that it is a ferroelectric, it has the ferroelectric polarization. Okay, so I'm going to explore on this composition, on this composites, bismuth ferrite, cobalt ferrite composites. Okay, so on this nanocomposites, as I mentioned, the lateral view will be like this. Okay, if an ideal material, like if we could prepare a very ideal material, you will be having a ferroelectric material on one side, and then ferromagnetic material coupled together, and the top view will be like a checkerboard structure. This is like an ideal structure, and if we could prepare a material like this is ideal, but due to practical problems, it is very difficult to have this kind of structure. I'm going to show what are the difficulties and what are the advantages if we have these kind of very clean materials. Okay, so how this magnetoelectric effect is produced on these nanocomposites. Okay, so if you give an input of a magnetic field, okay, due to magnetostrictive effect on the ferromagnetic material, so that is going to be strain on the ferromagnetic phase. Okay. So this ferromagnetic phase here, on this ferromagnetic phase, is coupled with your ferroelectric material. Okay. So that if it is coupled here, that is going to produce a strain on the ferroelectric material. Ferroelectricity, which is also a piezoelectric material, because it is piezoelectric, it can switch the electric polarization. So by applying a magnetic field, you can switch your electric polarization. Similarly, by applying electric field, you can switch your magnetic polarization. The inverse effect of this one. Okay, so the main parameter, the main thing here is the elastic coupling between these two phases. Okay, so this is very, very important. And on this presentation, I'm going to present in detail how this elastic coupling is occurring between these two materials, how we can tune that elastic coupling by different strain parameters, and then is it possible to measure this elastic coupling. So that's what we are going to see in this presentation. Okay, so we have prepared most of the forms which I'm going to present here were prepared by the pulse laser deposition, and I'm going to take only one composition, 30.35 cobalt ferrite, 0.65 bismuth ferrite. This is one of the composition which showed very good property. So we stick to this composition. We also tried other composition. On this presentation, I'm not going to present my results on a different composition. I'm going to stick whatever results I'm showing is only on this composition. Okay. So I'm going to on this presentation, I'm going to stick with the strontium titanate substrate one substrate, and these are the growth parameters which we maintained for an optimal epitaxial growth of these nanocomposites. Okay, so on a this is a simple cartoon which shows how in a pulse laser deposition your thin films are produced. You are having a krypton fluoride excimer laser where the pulses comes and falls on the target. So if you put a sample substrate at a heater, you can change the temperature. At a different temperature you can grow. So if you put the substrate on the heater, so you can produce epitaxial fill, and also you can maintain the environment. If you are working on oxides, you can maintain on oxygen, or if you are working on metals, you can work with argon or nitrogen, so that you can produce highly epitaxial and highly pure materials. Okay, so this is one of the this is the system, a lab system which we use, homemade pulse laser deposition. This is the laser, so homemade chamber, and this looks very simple PLD system, but this has produced a lot of nature paper and science papers also. The materials, the thin films prepared on this using this instrument has been collaborated with, as I said before, with the Nobel laureate Albert Fort also. So this is one of the basic PLD system. Very sophisticated PLD systems are available where you can insert your substrate. You can take out as a device, as a transistor or whatever device you need. But this is a very basic pulse laser deposition. This is inside your pulse laser deposition, the plasma is produced and the films can be and you can prepare your films here. Okay, so I'm not getting into the details of pulse laser deposition more than this. Okay, so let me get in how the thin films grow on a epitaxially on a substrate. Okay, so there are three modes by which your material will grow. One is called as island growth. If the material is not wetting properly with your substrate, it will diffuse slowly on a substrate, so it will form an island. Okay, and another one is called as a layer by layer growth, or Frank van der Merwe method. If it wets properly with the substrate, you can have a very nice epitaxial very smooth film. So if you are working on a single phase material, most of them will prefer this kind of growth method on thin film, so that your roughness will be very small, or your roughness will be almost the same as your substrate roughness. Okay, so there is one more growth method called a mixed growth method, where you can have both the island and then layer by layer growth. This is called as Stransky-Krasnov growth. Okay, so this growth difference between different materials on a substrate is the main parameter for these multiferroic nanostructures, which I'm going to concentrate now. Okay, in this slide, I'm going to show how spinel structure, cobalt ferrite, we all know that that's a spinel structure. So how a spinel grows on a perovskite substrate OO1. Okay, so the surface energy of a spinel is like OO1 and 111 is highly anisotropic. So it is a 111 oriented surface energy is almost 10 times that of OO1. Okay. So this surface energy matters for the growth. Okay, so the surface energy and then the surface area makes this spinel structure to grow as a pyramidal structure on a O1 oriented substrate. Okay. So if what will happen if you put one more material, perovskite material, on that one? Okay, so perovskite, as I said in the beginning, it is a cubic structure. So this is a O1 structure on a O1 substrate. This perovskite wets completely the substrate and grows layer by layer method. Okay, and if you put and the 111 phase spinels partially wet and grow as an island. Okay, so if you put both together, your perovskite will grow as a layer by layer growth, and then your spinel will grow as an island growth. Okay, so this is the reason why on a single substrate, your spinel structure, your spinel will grow as a rod, and then your perovskite grow as a matrix layer by layer. Okay. On the other hand, if you inverse or if you change the substrate to 111 orientation, okay, so the perovskite, the spinel will wet completely, as I said in the previous slide. The surface energy is different for spinels on the 111 plane. Okay, so the spinel will wet completely. So the spinel will grow as layer by layer, and then your perovskite will wet partially, and then will grow as a column. Okay, so just by changing your substrate orientation, you can change whether you need a cobalt ferrite or a spinel column, or you need a perovskite column. Okay, whether you need a ferroelectric material as a rod, or whether you need a ferromagnetic material as a rod. Okay, so this So what are the parameters which are important to have this ferroelectric, ferromagnetic orientations for the elastic coupling? Okay, one is the orientation, as I said before, and then whether the interface is coherent or semi-coherent. Okay, you can't have a incoherent. Okay, already I said these are all epitaxial films. So if you have an incoherent interface, you will be having amorphous material. So either it should be a coherent or a semi-coherent interface. Okay. So how to verify this elastic coupling? How we can verify this that there is an elastic coupling between your ferroelectric and the ferromagnetic material? Okay, so indirectly we can do by measuring the magnetoelectric coupling. That is what people have done. That's what I have shown on the first one. But can we do it directly? That's what I'm going to tell now, and what are the difficulties on that one? Okay, directly by studying different strain parameters. Okay, so there are some theoretical attempts to show that the residual strain. Okay, so these are all theoretical papers. Okay, so but there are no experimental work. So we tried to show that to measure the strain experimentally and directly. Okay, so on a over one substrate, this is the X-ray plot. Okay, between 20 and 100. Okay, so these are all the highest peaks on the substrate peaks. Okay, so if you enlarge this region, it looks it looks like this. Okay, so you have a substrate peak, you have your cobalt ferrite peak, you have your bismuth ferrite, you have. Okay, somebody is raising hand. So can I answer now? Do I have to answer now, or can I answer at the end? Okay, so I will answer. If you have any doubt, I will answer at the end. You can always interfere. Okay, so you can always ask. Okay, so let me finish it quickly. Okay, so on the bismuth ferrite part, you have two peaks. One is a strained peak. One is called as a strained, and another one is relaxed one. Okay, so apart from that, this is pure. So you have epitaxial film. So if you have a 5 scan, you can clearly see that your bismuth ferrite and cobalt ferrite goes cube on cube growth. So it is growing epitaxially. Okay, so there is no confusion on this one. Okay, so this is the A.V.M image. It shows a very nice nano rods. This is the spinel rod on a perovskite matrix. Okay, so these are all nano rods on a perovskite matrix. Okay. So this is the low resolution TEM image. So the cross section shows that the interface is not as clean as we expected. Okay, so in the first slide I showed a cartoon. Okay, so I think we can annotate. Okay, so the interface is not very clear. That is why the elastic coupling. That's why we can't have that 100% elastic coupling. You can see that the interface is a very rough. So this is self-assembled or spontaneously grown. So we can't control on this one. Okay, so we need to work on this one. Okay, so how this lattice strain, okay, so works on. Okay, so the lattice parameter of bismuth ferrite is 3.96, and the lattice parameter of strontium titanate substrate is 3.905. Okay, so the bismuth ferrite has a larger lattice parameter than the substrate. So what will happen if is there will be a in plane compression to maintain the volume. There will be an out of plane expansion. Okay, so if you grow bismuth ferrite alone on a strontium titanate substrate, this is what will happen. So there will be an in-plane compression and the out-of-plane expansion. Similarly, the lattice parameter of cobalt ferrite is 8.3. So if you take up two unit cells of perovskite, strontium titanate, so you will be having again the cobalt ferrite lattice parameter will be larger than two unit cells of strontium titanate. Okay, so again, what will happen is you will have in-plane compression, and then the out-of-plane expansion here. So if we grow these things alone, okay, but what will happen if we grow together? Okay, so if you go together epitaxially, so we are having one additional interface here, okay, so between your spinel phase and the perovskite phase. So this additional interface plays a major role in the elastic coupling. Okay, so we wanted to measure that strain, the interface between spinel and then the perovskite. So we measured the in-plane lattice parameter, but unexpectedly, for cobalt ferrite, it shows the in-plane is relaxed and out-of-plane is compressed. Okay, and also for bismuth ferrite, as I shown, there are two graphs. Okay, two cases where one case the bismuth ferrite is strained, and in another case your bismuth ferrite is relaxed. Okay. So this unexpected thing where your cobalt ferrite is relaxed in plane and compressed out of plane is because due to the elastic coupling between your bismuth ferrite and cobalt ferrite here. Okay, so as because of this interface between your bismuth ferrite and cobalt ferrite, which are elastically coupled, the bismuth ferrite pulled the cobalt ferrite to accommodate itself here. Okay, so that's what is said here. The cobalt ferrite strain is appear to be the elastic deformation caused by the bismuth ferrite. Okay. How this elastic coupling occurs, so I don't want to get into the details. Okay, how the strain varies when you vary the thickness of the film. Okay, so if the film is like a 10 nanometer thickness, you can see only the strained bismuth ferrite occurs. This is the perovskite phase, only the strained parameter occurs. So when you increase the film thickness, slowly the relaxed portion comes out, and films above 200 nanometer, so you can see the film is completely relaxed and the strain portion is missing, okay, or a very, very small strain portion. But the cobalt ferrite remains as such, compressed. Okay. So now this is the magnetic force microscopy. So this shows clearly that the nanorods are magnetically polarizable. Okay, so I don't want to get into the details because of our time constraint. Okay, so this again shows that the magnetic polarization can be switched. Okay, so this is the clear confirmation that the rods are magnetically polarizable. Okay, and this is the piezo force microscope. This clearly shows that the prepared films are ferroelectric material, and the ferroelectricity remains even after 5 days. So this clearly shows that it has a robust ferroelectric material with ferromagnetic property at a room temperature. So this is this confirms that it is has the multiferric properties at room temperature. So this is the magnetization and also the KER, which complementary magnetic measurements, which clearly shows that the EC axis, we can switch the EC axis from over 1 to 111. Okay. So now I will move to the second part, which is the how the strain can be tuned. Okay, so in the previous part, I explained how the lattice substrate, strain affects the growth. Okay, so in this part, I'm going to tell you how this strain affects your crystal structure. Okay. So this is a cartoon where the commercially available substrates with their lattice parameter here. Okay. So all these materials which are mentioned here are perovskite structures or double perovskite, mostly perovskite material. Okay, so you can grow epitaxially these materials, whether you need a conducting material or you need a insulating material or a magnetic material. Okay, so on these substrates. Okay, so as I mentioned, the strontium titanate, the lattice parameter will be around 3.9. So if you want to put a tensile strain, you can use either MgO or magnesium aluminate substrate, which are having the lattice parameter around 4.1 or 4.2. Okay, so if you put a bismuth ferrite, for example, which is having a lattice parameter 3.9 on this substrate, this will have a tensile stress. Okay. On the other hand, if you put on the lanthanum aluminate substrate, it will have a huge compressive strain. Okay, so these are some of the vertically aligned nanocomposite which can be grown epitaxially. Okay, so if you see one component of all these things will be a perovskite structure, either bismuth ferrite, A.V.V.M titanate, or lanthanum strontium. Okay, so this is because the perovskite are highly it can simple structure, and it can have so many properties. So you can create many properties, emergent properties, by combining different material with the perovskite structure. by changing the tune, the strain along vertical axis and the strain along the horizontal axis. Okay. So how the strain affects the ferroelectric material, a different ferroelectric material or perovskite material, as shown here. The lead titanate is one of the well-known material and robust material. So without any strain, this is the ferroelectric Curie temperature. So above this temperature, this will be paraelectric, and below this temperature, this will be ferroelectric. So if you apply a compressive strain, the phases will change. Okay, from C phase ferroelectric to R phase ferroelectric to AA phase ferroelectric. If you apply tensile strain. Okay, so the strain, these are all the in-plane strain parameters. Okay? And this is the temperature in the centigrade scale. This you should remember. Okay. Again, if you look at the barium titanate, you see if the in-plane strain is very small. Okay, when you compare with the lead titanate. Okay, so even for a minute strain, so this is the Curie temperature here for ferroelectric Curie temperature, transition temperature for barium titanate, okay, which is around 120 degrees centigrade. So at without any strain for a bulk material. Okay, so if you apply compressive in-plane strain, it changes to tetragonal structure. But if you apply tensile stress, it changes to orthorhombic, and then this is a combination of monoclinic and orthorhombic. So you can play a huge part by changing the strain, okay, in plane strain. By changing the substrate strain, you can have a tetragonal structure, or you can have orthorhombic structure, or you can even have a monoclinic structure. Okay, so this is one of the phase diagram for well-known quantum paraelectric material called strontium titanate. Okay, so you can clearly see the in-plane lattice strain here, how small it is. Okay, so here it is on the order of -5. For barium titanate, this is on the order of -1, and for the strontium titanate, this is like 100 times less than the barium titanate. So if you slightly change, the strontium titanate is so unstable quantum. That's why it's called as quantum paraelectric. The quantum effect starts playing on this material. Okay, so if you slightly change the strain, you can change from orthorhombic or tetragonal or monoclinic structure. And you should remember, you should note down the temperature here is in the Kelvin region. Okay, in the Kelvin scale, not on the centigrade scale. This is on the Kelvin scale. So all these are below room temperature, and at 0 Kelvin, this is called as a quantum paraelectric material. I don't want to get into the details of quantum paraelectricity. Okay, so this is how we can tune the material property by applying in-plane strain. Okay, so I'm going to use these are all theoretically worked out material. So how this is going to affect my material, okay, bismuth ferrite. I'm going to check it out. So this I have explained already in the last part. So what will happen if I change substrate from strontium titanate to lanthanum aluminate? Already I mentioned on the first slide that the lanthanum aluminate is has a lattice parameter of 3.79, okay, which is having a huge compressive stress. Okay, so will it grow epitaxially with that much huge lattice strain? You could clearly see that around 4.4% for perovskite and around 10% for spinel phase. Okay, but there are some theoretical report and also experimental reports available for a single phase material that this is possible, that this is possible. Okay, so on this graph, okay, sorry. Okay, so this XRD plot shows us a thin layer of lanthanum aluminate. Okay, a thin layer of lanthanum nickelate will produce a normal rhombohedral structure of bismuth ferrite. Okay, so if you remove this lanthanum nickelate and if you grow your perovskite bismuth ferrite directly on your lanthanum aluminate substrate, you will be having a very small rhombohedral structure, but a huge tetragonal structure comes out. Okay, so this is quite new. Okay, because on a bulk scale, your bismuth ferrite will always be in the rhombohedral structure. Okay, by changing the in-plane lattice strain, you can tune from the rhombohedral structure to tetragonal structure. Okay, so I will just quickly show this A.V.M graphs, which are very clean nanorods are seen, and you can clearly, this is the cross-section TAME, which clearly shows that the interface, we can have a clean interface of a bismuth ferrite and a cobalt ferrite. Rather, when you put on strontium titanate, the cobalt ferrite was not growing this much clean. Okay, so by changing the substrate, by changing the lattice strain, we can tune the crystal structure of perovskite, and also we can have a very clean interface, which will improve your elastic coupling between your ferroelectric and ferromagnetic material. In turn, that will improve your magnetoelectric coupling. Okay, so this is again the A.V.M images for films grown at different temperatures. Okay, so on our optimal growth temperature, you can see clear O1 oriented spinel on a very clean matrix. But if you increase the temperature, there are some 111 oriented rods also. Okay, I'm not going into the details of the growth parameter. Okay, so if you, what will happen if you change the strain? Okay, so if you have strontium titanate, you can clearly see the rhombohedral perovskite matrix. Okay, and then if you have a more compressive stress, that changes to tetragonal structure. But if you have a tensile stress, this will to grow epitaxial film is very difficult because of huge tensile stress. They are growing. The bismuth ferrite decomposes and grow like a dendritic growth method. Okay. So we wanted to measure directly the strain. So what we tried is, as I said before, we have on this structure we have two types of crystal structures. One is a spinel, and another one is perovskite. And spinels are highly resistant to chemical etching. So we tried to chemically etch the perovskite part, and then see how this elastic strain was on the cobalt ferrite part. So after etching, we were expecting that almost all your bismuth ferrite perovskite matrix was removed, so you will be having only the cobalt ferrite material. So this is the experiment we tried. So let us see, this is the SEM image of original sample. So you can see the matrix, and there are some cobalt ferrite matrix here. So the cartoon is something like this. So you have a bismuth ferrite matrix here with a cobalt ferrite rods. Okay, so after etching, you could clearly see that we have etched the bismuth ferrite part almost completely. You couldn't see any matrix part on this same scale. Okay, so you could only see the cobalt ferrite rods here. Okay, so these are the same samples. So that means we could etch bismuth ferrite perovskite alone with different etchings. Okay, so this is the backscattered SEM image, which clearly shows that we have removed bismuth ferrite. Almost we have removed it. Okay, and the EDAX pattern shows that the bismuth ferrite has completely reduced after after etching. Okay, so this is the DAX pattern before etching, and this is the DAX pattern after etching. So this has completely removed this bismuth ferrite. Okay. And the XRD pattern before etching, we could clearly see that there are relaxed and strained portion, but after etching, this relaxed portion is completely removed, but still there are a small portion of the strained bismuth ferrite exists. Okay, so but there is no change in the lattice parameter, or a very small change in the lattice parameter of out of plane lattice parameter of cobalt ferrite. So still we couldn't confirm that the residual strain is in cobalt ferrite is elastically coupled, because we cannot completely remove this bismuth ferrite. Okay, so that is the reason. Okay, so the conclusion of this part, okay, so all the lattice strains have been measured. So cobalt ferrite is plastically removed. So this is still in doubt, but strained in the vertical direction. Okay, and the residual strain, this is on cobalt ferrite. We could not prove surely that it is not elastic, because we could not remove the bismuth ferrite completely. So still it is doubtful. If we could remove somehow the bismuth ferrite completely, then we could show that these are all elastically coupled and the residual strain is there. Okay. Coming to, I will quickly finish this interface engineering part. Okay, so this strontium titanate is a band insulator. Okay, so both strontium titanate and lanthanum titanate are band insulators. With strontium titanate, the band gap is around 3.2, and for lanthanum aluminate it is around 5.6. But if you put this lanthanum aluminate on a strontium titanate substrate, if you grow epitaxially, okay, so it shows a superconducting property. Okay, so this is the resistance versus temperature, which shows superconducting. Okay, and both strontium titanate and the lanthanum aluminate are not magnetic. But if you put it together, and because of the interface, this shows a ferromagnetic property. So this interface on the nanomaterial plays a very major role. You can expect the unexpected properties on the bulk. Okay, so how this superconductivity occurs on this lanthanum aluminate strontium titanate interface. Okay, so let's just quickly see this, and then we conclude. Interface. So on a strontium titanate, you will have on a single crystal, you will be having one layer of a titanium oxide layer over strontium oxide layer. Okay. So this is in charge wise, this is neutral. So you will be having strontium 2 plus and then oxygen 2 minus. Titanium 4 plus will be oxygen 4 minus. So this is charge neutral. Okay. On the other hand, if you take lanthanum aluminate, lanthanum is 3 plus, oxygen is 2 minus. So you will be having plus 1 state here. Okay, so here aluminum is 3 plus, oxygen you will be having 4 minus. So you will be having minus 1 charge here. So this is what is shown here. So you will be having 0 charges on the strontium titanate, but when you go to the interface, there is a sudden jump for lanthanum aluminate. This will be having a plus 1 and minus 1 layers. Okay, so there is a charge catastrophe. Okay, so the electrons at the interface between your strontium titanate and the lanthanum aluminate will move like a gas. Okay, and that induces the superconductivity. Okay, and the difference between the charge difference between these two induces the ferromagnetism also. Okay, and quickly complete it. Okay, so you can change strontium ruthenate or strontium iridate superlattice. Both of them are non-magnetic, but if you prepare a superlattice pearl, you can see the ferromagnetic property evolving from non-magnetic material because of the interface. Okay. So when you are working on a nano materials, a very thin material, so interface do mind. Okay. So at the end, I want to conclude with one of the well-known quote of Nobel laureate Herbert Kromer during his Nobel lecture on 2000. Okay, so in future, the interface is going to be the device. Okay, 100 years back, the interface was devil. Now the interface is going to be the device. What about devices which we are going to use? We are going to use the interface as one of the device. Then only we can reduce the size of your electronics. Okay. So with that, I will conclude my presentation. I thank you one and all. And sorry for the inconvenience for the network problem. Okay, so if you have any doubt, yeah, I'll be happy.
Excuse me, sir.
Yes.
Good afternoon. I'm Renuka from National College. How could you reduce the strain, sir, by chemical method or any other physical method?
On my presentation today, whatever I presented, I was presenting on the strain due to the lattice substrate and the full.
Lattice substrate means?
Okay. Sorry for the discontinuity again. So whatever I presented here is the strain between your substrate and the film, the strain between two materials if you put together elastically. But you can use this strain but by chemical doping. So you put a material, chemically dope material on the lattice with a different size. You can induce that strain, whether it is a tensile strain or a compressive strain. You can induce it chemically. That is possible. Yeah.
Yeah. In that case, how could I know whether I'm doing the particular element doping is perfect or at what concentration I have to dope? Then only I will get the particular desired strain I can get.
For that, you should have some idea about your material and what you are doping, whether it is charge, the charges are the same or this, whether the size are more or less some idea about your material and what you are doping. You cannot dope a small element with a huge element. You cannot produce a huge strain. In that case, the second element will form as a secondary phase. It won't get into your lattice. That will go outside the lattice. So you can't dope it. It will be a secondary phase that you can that you can see in your X-rays. Okay, X-ray you can if there is a secondary phase, you can that.
Through
and
XPS also we can find out, sir. Through XPS also we can find out whether the secondary phase is present or not.
You can find out whether the material is available, but you don't know whether it is on the lattice or on the outside. XPS doesn't say that, I think. Okay, so using XPS, yeah, you can find out whether your material is on what electronic charge it is there. Whether, for example,
it is an electronic state, we can find out the electronic state. Okay. Regarding etching, HCl etching and all, you. Hello, sir. Hello.
Yeah. Tell me.
Yeah. Regarding HCl etching, you told me no, sir. That HCl etching, just we have to keep our component or that thin film in the HCl and it will all go off, or you have to go for any the famous physical etching like lithography. for lithography or simple?
No, it's a simple chemical etching because we are having two types of crystal structures there. One is a bismuth perovskite structure, and another one is a spinel structure. So both of them will chemically etch differently. So we use a simple chemical etching.
Okay, sir. Yeah, formed spinals and some other cobalt something and all that is in oxygen in O3, but spinals in O4. In that case, is it possible to form nanocomposites, sir? You did not find any difficult, sir?
Material. So if you prepare the composition with the proper oxygen atmosphere, so you can do that. Okay, so this was on a thin film. Okay, so we prepared a target ceramic, which is the combination of which contains both cobalt ferrite and bismuth ferrite. Okay, one is an O4 and another one is O3. It is the target contains both. But as I explained at the beginning, when you prepare a thin film, the perovskite will grow differently, and your spinel will grow differently. Yeah, spinel. Okay, so it will grow differently, and in oxygen atmosphere, you can maintain that oxygen.
Oxygen maintain. By spin coating or some other method you have used, sir? Sir, spin coating or some other coating method you have used? PVD method you have used?
I used a pulsed laser deposition method.
Okay, sir.
To prepare these epitaxial thin films, but if you can prepare it as a ceramic, as a polycrystal. But if you want to grow on low cost thin film technology like a dip coating or spray coating, then it is a bit difficult. But you can still try. These two are two different. It will segregate. It will not combine. The spinel and perovskite will not combine. So it will grow two different phases.
Okay, sir. Thank you, sir. Thank you for your nice presentation.
Thank you.
Hello.
Yeah. Yes.
Yeah. So, what type of strain in epitaxial interface due to grain interface?
I couldn't get the question, sir. What type of strain and epitaxial?
Strain can be cast because you are preparing your material the form of epitaxial layer. Am I right?
Yes, sir. Yes, sir.
In such a case, there is a formation of grain interfaces. So the grain interfaces for each layer. So that grain interfaces can also causes a change in strain in what sort of?
If it is that is as I said before. So you should have a idea about the substrate lattice parameter and your thin lattice film lattice parameter. If these two are, there won't be any interface. There will be one interface between the substrate and your film, and it will grow as layer by layer because your film is not having any strain over. Okay, so if you put a more strain, then, as you said, you will have another interface. It will form a domain, a thermal form. It will try to reduce its energy to form as a domain. So you will have another interface there. That's how it happened on island level. So it depends on your thin film, your substrate lattice parameter, and your material lattice parameter, and the elasticity of your material also. If your material is highly elastic, you can give more material and the substrates. Hello, yeah, can I answer that question, sir?
Yes, okay, understood. Thank you, sir. Thank you.
Thank you, sir.
Clarifications from participants.
I can't get you. I can't get you. Can you repeat the question, please?
Is there any clarifications from participants? Is there any?
To deliver the vote of thanks.
Thank you. On behalf of PG and Research Department of Physics and on behalf of organizing committee, entire college, I may like to express our sincere thanks to research person for more effective and informative lecture on emergent properties of self-assembled nanocomposite. And my special thanks to our respected secretary and correspondent, principal, coordinator for giving us a moral support. And I thank all professors, researchers, and students for their active participation. Thank you very much. Thank you all.
Thanks a lot. The class was really great.
Thank you. So if you have any doubts and